Hello, my name is Alex, and this is my AE 1601 glider project report. Our goal with this project was to use all of the knowledge we've gained over the whole class and the engineering design process to design and fabricate a balsa wood glider. I've named mine the Warhawk. These are the design requirements of the glider. First, it must be made primarily of balsa wood with some materials found around the house. It has to fit inside a 16-inch by 16-inch square box. It has to fly at least 20 feet thrown by hand and on a level ground, and it must not break when landing after the flight is over. My initial design provides a good baseline with a rectangular main wing, a horizontal stabler and vertical stabilizer, and a single little ball of clay for a weight on the nose. This allows for easier calculation of flight parameters like aspect ratio and center of gravity, as well as quicker construction. The initial design comes from a balancing of a few requirements and criteria of a stable flight. First, the overall dimensions are restricted by the box it has to fit in, a 16 by 16 inch box. Since the lift is related to the wing area, making the wing just barely smaller than the box maximizes the lift force, allowing for a longer flight theoretically. The first design choice I had to make was what material to use for my glider. I had three main options: cardboard, balsa, and 3D printed plastic. Cardboard was good because I had a lot of it, it's easy to cut, and I can bend it and it won't break. Balsa is good because it's lighter, has barodynamics and a smoother surface, and it's stiffer so it keeps its shape better. For these reasons, I decided to use cardboard for the prototyping phase and balsa for the final glider. Since 3D printed would take too long to design and print, I decided to not use that for either. The next design decision I had to make was what shape to make my wing. I drew 5 different possible wing shapes, and I tested each one by throwing it with my cardboard prototype glider. The one that ended up working the best was the straight leading edge and tapered trailing edge, and that had an average flight after 11 throws of about 30 feet, while the others had less than 28 feet. The final design decision I made was on the dihedral angle. When I went out initially with my glider, I had no dihedral angle, and it went at about 20 feet on average. Then I added a slight dihedral, and it increased to 25 feet on average. And finally, I increased the angle even more, and it went up to 32 feet on average, which was a big improvement from the 20 feet from before. When I was test flying the cardboard prototype glider, I noticed that it was still a little bit out of balance with the center of gravity behind the wing a little bit. So to fix that, I moved the wing backwards, and that allowed me to reduce the weight of the nose plate quite a bit. That in turn fixed the balance issue, and it allowed the glider to go much further than it had been going. After a few more hours of tuning the control surfaces on the main wing, I was able to get a last flight of just over 50 feet with the dihedral angle and the wing pushed back and the nose with reduced weight. Once I'd locked in the flight parameters and design of the glider, I was able to start construction on the final balsa wood glider. After I finished construction, I balanced the glider and ended up with the center of mass directly over the quarter chord line. However, unfortunately, I noticed that the piece of balsa I was using for the main wing had a slight warp in it, so I had to use duct tape to add control surfaces to offset the lift generated by that one side of the wing.
All right, recorders ready? Okay, go ahead, you're up. Not bad. Not bad, not bad. Okay.
Now, Does the Warhawk meet the requirements of the project? Well, it flew at least 20 feet. In fact, it flew 43 feet. It is made primarily of balsa wood. It did not break on impact with the ground, and it fits into the 16 by 16 inch square box. Finally, I estimated the coefficients of lift and drag of the Warhawk. I used the equations shown to the right and the values I measured and calculated to come up with a average velocity of 22 feet per second and a coefficient of lift of 1.34. Then I calculated an aspect ratio of 3.5, a coefficient of induced drag of 0.18, and a coefficient of drag of 0.36. Overall, I thought this was a really fun project. I stuck with my original desire to design based on my own experimentation and doing as little research as possible. However, there are still a few ways that I can improve upon my design. The first is to reduce the weight of the fuselage. The wooden shaft I used was very bulky and did not need to be a square extrusion throughout the entire length of the fuselage. A second thing I can improve is the aerodynamics of the nose. The weight system that I have is not very aerodynamic at all. These are my sources. I used Aero Toolbox to get ideas for playing wing shapes, and I used the provided Word document for estimating lift and drag coefficients.